We're going to talk today about this thing called the normal distribution, which right now that thing just looks like a ghost to you, but we're going to work up to that, and by the time we get back to it, you're going to say, that's no ghost, that's a valuable statistical tool. But before we get to that good stuff, let's think about some of these things that we've done in the past. What I have right here is a dot plot that is showing the various hourly wages of high school students. So we have 3 students who made $8 an hour, and then we had 2 students who made $16 an hour, 1 student who made $12 an hour. Well, if I were to form all of this data into a list, I would have 3 8s, a 10, 2 11s, a 12, a 13, 2 15s, and 2 16s. Well, I could take that list and I could put it into Desmos or another calculator and find the mean and the standard deviation of those numbers. Now, you don't necessarily know what the standard deviation is yet, but you do know what the mean is, and both of these items are going to be very important for our normal distribution work. So knowing that we'll come back to standard deviation, let's just take a look at this distribution of dots. And there's nothing that remarkable about it, but I'm going to compare it to maybe a different survey we might do of a different group of high school students. And what if the survey of their data turned out to give me a dot plot that looked like that? Well, now this is a different story because this dot plot seems to have quite a bit of a different pattern or a shape than the previous one. If you compare these two, kind of spread out, but this one kind of, if I would to outline the dot plot, would form, and I'm going to do this really lightly here, kind of a shape like that, which, by the way, should remind you of this thing called the normal distribution that we saw earlier. Very frequently in this world, the data that you gather will follow a normal distribution. It's something that just seems to happen in many, many instances, and it happens so frequently that a whole branch of statistics or mathematics is devoted to studying this thing called the normal distribution. So everything we're going to talk about the rest of the way on this video is assuming that the data set that you're working with is following the shape of this normal distribution. So I had mentioned a couple times the standard deviation. So for example, in this setup here, we had a standard deviation of 3.1. And in this set right here, we had a standard deviation of 1.7. So what is standard deviation? You can think of standard deviation as how closely or tightly packed the data is to the center. So in this case, the average wage was 11.9 or $11.90. That happens about right there. And in the normal distribution, the mean is going to be exactly in the center. This is roughly in the center. But if you'll notice, most of the students were making a salary or an hourly wage very close to the mean. So my standard deviation was smaller, like 1.7. In this other example we had here, you'll notice that the student's hourly wage is spread out. It's not packed around the center. I'm going to draw a line again at about $11.90, and you'll notice that those dots are spread out, or those student wages are spread out, and thus we have a larger standard deviation. So for right now, you can think of standard deviation as simple as this. If a standard deviation is larger, the data is more spread out, and if a standard deviation is smaller, the data is more tightly packed around the center or the mean. So when we work with a normal distribution, especially if it's perfectly shaped, you will know that the mean is always going to fall in the dead center. And the standard deviation is going to represent how spread out the data is. And so what we'll do is we'll usually draw a slash about here and about here. This is one standard deviation, so I put plus one standard deviation away. And over here would be minus one standard deviation. Then we can go out two standard deviations. Now I know that might be confusing for you right now, the standard deviation thing, and it's going to make more sense when we do more examples. But just know right now that mean is in the dead center of your normal distribution, and standard deviation is how spread out you are from the mean. So here's an example that might make it a little bit more clear. Hospitals keep track of the birth weight of babies. So let's say over the last year, the mean birth weight was 8 pounds. That means 8 would go right there in the dead center. And like many things in this world, the birth weight of babies is probably going to follow a very clear normal distribution, meaning that if you were to turn each baby's birth weight into a data point and make a dot plot out of it, it would follow something like that, where we would have many babies around 8 pounds, but as I got out to a larger weight or a smaller weight, there's fewer and fewer babies. So if the mean is 8 pounds and the standard deviation is 1 pound, that means this would be plus 1 standard deviation, and this would be plus 2 standard deviations. That would be minus 1 and minus 2 standard deviations. So you should always envision that there's a bunch of data points that are dots right leading up to this so that you get this shape that I showed you earlier. Each of those data points represents a baby's birth weight. And of course, not every baby is born at 8 pounds or 9 pounds. There's plenty of babies born at 8.5 pounds, 8.25 pounds, 8.75 pounds. But this would be a normal distribution with the mean and the standard deviation of 1 pound. But we can apply that to a different situation. Let's say a company is analyzing how many miles a set of tires will last a car owner. So the mean would be, in this case, 48,000, and the standard deviation would be 7,000. Now your normal distribution would look different. I've erased the previous examples data, and now we're going to say the mean is 48,000, and the standard deviation can help us. We say 48,000 plus 7,000. That would make it 55,000 and 62,000. And then I can go minus 1 standard deviation, which means I subtract 7,000, and I subtract 7,000 again. So that means if I were gathering data about these tires, a few people would have had their tires last only about 34,000 miles. Many people would have their tires last about 48,000. And some would have their tires last 55,000. Of course, there would be all these dots or data points in between. Someone might have their tires last 51,000 or 54,000 or 47,000. So this is just giving you a rough picture of what the distribution looks like. Now, since many things in the world follow the normal distribution, the math people have come up with the empirical rule, which is a way for you to estimate with the normal distribution. And the empirical rule goes like this. As long as you know your mean and your standard deviations, and you would put numbers onto there so that it made sense for the context of the situation you're in, then you know by the empirical rule that 68% of your data is going to fall between the 1 and -1 standard deviations, meaning 34% of the data roughly would fall in each of those compartments. So if I wanted to know how many or what percent of tires lasted between 41,000 and 55,000, that would be 68% of the tires. Or 34% of the people would have their tires last between 48,000 and 55,000, and about 34% of the people would have it last between 41,000 and 48,000. Then we would also go on to say 95% of the data falls within 2 standard deviations of the mean. So basically, most of your data is going to fall between 2 standard deviations plus or minus from the mean. Now there can be a far more complex set of calculations. These are just estimating rules of thumb. So for us right now, you just need to know 68% of the data falls within 1 standard deviation of the mean, and 95% of the data falls within 2 standard deviations of the mean. So let's talk about donuts. Let's say the Tim Hortons management is keeping track of the number of donuts they sell each day so they know how to be prepared for future days. And they find out that the donuts follow a normal distribution and they have a mean of 420 and a standard deviation of 50. As long as they did a dot plot to find out if the data followed a normal distribution, and they found out that it did follow a normal distribution, then they can start making this little sketch. The mean is 420, the standard deviation is 50, so I can add and subtract 50 from the mean, and in fact I can go out one more standard deviation, so now I can just look at this, and as a Tim Hortons manager, I can know that there's a 68% chance that I'm going to sell between 370 and 470 donuts in a given day, because the normal distribution tells me 68% of the data falls between 1 and -1 standard deviations from the mean. So right away I could answer this question. 68% of the days they sell somewhere between 370, that's 1 standard deviation below the mean, to 470 donuts, because that's 1 standard deviation above the mean. The 68% is the general estimation rule from the empirical rule. We could change the question. What percent of days do they sell between 320 and 520 donuts? Well, when we built this distribution, we used the second standard deviation and the second standard deviation by adding 1 standard deviation and then another, subtracting 1 standard deviation, then another. And the short answer to this is 95% of the days they should sell somewhere between 320 and 520 donuts. So if they look at the records and on a certain day they sold 270 donuts, they should know that that's a very unusual thing and maybe look into what happened that day, because 270 donuts is well below 2 standard deviations less than the mean, and that's telling you something weird happened. Now the questions for estimation can get more complicated. For example, what percent of the days do they sell more than 470 donuts? Well, here's our 470, and I want to figure out what percent of the time do they sell more than that. It's kind of difficult, but you can do this. You know that 50% of the days are going to be less than the mean, so there's 50% over there, and there's 34% here, so I know this. 50 plus 34 is 84% of the time they sell fewer than 470 donuts. If 84% of the time is fewer than 470, then we can do the math. 100% of the time minus the 84% of the time that they have fewer than 470 donuts leaves me 16% of the time that they sell more than 470 donuts. So this one's getting a little bit more complicated, but you can get many more complicated questions about the normal distribution. In fact, you can take an entire math course about the normal distribution. It is that important and it is that common out in the world.